Hi everyone, welcome back to Dave's Math Channel. I guess you can tell I'm a little bit sick. I got a little bit of a hoarse voice. I think I'm coming up with something, but I'm still gonna do this video. Anyway, this is another video on practical math. Today I'm gonna talk about musical scales, the mathematics behind music we're all familiar with, in particular the 12 semitone scale of Western music. Um, and so let's begin. Um, so how do we develop a mathematical theory of music? Well, it's pretty simple. As you know, music is based on sound. Every music's based on notes of the musical scale, and every note has a particular frequency. It's a sound wave with a particular frequency. The frequency defines the note. For instance, I believe there's A440, the middle A of a piano is usually 440 hertz or 440 cycles per second. And I think middle C is usually around 260 or 256, depending on what kind of scale you're using. But every note has a frequency. That's the first thing you should know. And then so who came up with who was the first person who came up with the mathematics behind music? Well, I think we can trace that to Pythagoras. Pythagoras, not too much is really known about his real life. He was an ancient Greek. He lived around 500 BC. He talked about what he called music of the spheres. He basically thought that the world or the universe, I guess we didn't know much about the universe then, but what we knew about the world, he thought it was governed by mathematics. Pretty brilliant insight, I think. And, he thought there was simple math, there was simple ratios involved in everything. And that's particularly true in music. He discovered, his own musical scale, basically. Here's what he discovered. He discovered the law of harmonics, which is a very basic idea in music theory. Just think about a vibrating string. It might be helpful to think of a violin string or a guitar string. So, you have these harmonics. The first harmonic is just one half a wavelength between the two ends of the string, which are called nodes because the string's not vibrating there, but it's vibrating at the maximum in the middle. So that's what's called a antinode in the middle, where the amplitude's highest. So you can see that the first harmonic is just a low C, which is corresponds to half a wavelength. And I probably should have. I think it is on the slide with the yeah. So you notice the wavelength is just the length of the sound wave. Sound is a compression wave. That's another thing I think I should have mentioned. Sound is what's called a longitudinal wave, and the way sound works is you get compressions and rarefications of air molecules, and those compressions actually move. They move like a wave, um, and they have a wavelength, which is just the distance between two crests, two maxima. And then there's frequency, which is the number of cycles per second. And it turns out the wavelength times the frequency is equal to the speed of the wave. That's pretty easy to prove. But so there's an inverse relationship between wavelength and frequency. So notice what's happening here. The first harmonic has its wavelength is twice the length of the string, or if you like, half the wavelength is the length of the string. And then for the second harmonic, there's two um, antinodes in this case. There's three nodes. There's a new node in the middle. Now you've got one wavelength. So notice that the wavelength is now half of what it was before. But first, the wavelength, or if you like, half the wavelength was the length of the string. Now half the wavelength's half the length of the string. So from going the first stars to second harmonic, we've decreased the wavelength by a factor of two, which means since frequency is inversely proportional wavelength, that means we double the frequency. And then the third harmonic, that just involves three antinodes, that's the G. That's going to be three times the fundamental frequency, or if you like, three halves times the second harmonic. So there's actually an interval called a fifth here, going from C to G. That's a ratio of frequency of three halves, or 1.5. And I think you can see how this works now. So now, by the time you're up to the fourth harmonic, you've quadrupled the frequency that you started with. So this is now two octaves. Remember, an octave is a factor of two. And it's interesting because octaves sound like the same note. I mean, we say they're the same note, and they basically are. They're just different by factors of two, powers of two. So our ear kind of imagines that powers of two in frequency are the same note. Kind of interesting. Um, but I think that's a psychological phenomenon. And we like pleasing ratios. I mean, octaves sound like the same note, fifths sound pleasing. If you hear a C and a G together, doo doo, doo doo, that sounds harmonious. And then there's other pleasing ratios like fourth. A fourth is going from G to C, so that would be doo doo, doo doo. I can't really do it. It's hard to do it on my doo 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 doo. Yeah, that's better. So a fifth would be doo doo. That's a fifth. And then a fourth is doo doo. Goes to the next octave. So that sounds pleasing, right? When we hear these ratios, it sounds like music. That's what Pythagoras discovered, basically. And there's another ratio, the third, that's going from C to E. That's just two major notes. So do 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 do. I can't really do it. Do 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 re mi do do. That's a third. Yeah. So anyway, you get the idea. These harmonics produce pleasing ratios, and we can go up to the eighth harmonic. After we get past the eighth harmonic, they don't sound pleasing anymore. It starts sounding like noise, which is another interesting phenomenon. So if you do the first eight harmonics and you play them all together, it sounds like music. But if you go beyond the eighth harmonic, it starts sounding like noise. Interesting, I think. But anyway, so what Pythagoras did after he discovered these pleasing ratios is he came up with basically the same scale we have today. But this is what's called the Pythagorean musical scale. It involves 12 semitones. I mean, I guess eight notes, including low C and high C, C, D, E, F, G, A, B, C. I guess we call those do, re, mi, fa, sol, la, ti, do. Uh, so you know what those notes sound like. And then we don't only have we have two different size intervals between notes. We have whole tones. I guess that's C to D, that's a whole tone. D to E is a whole tone. E to F is a semitone. Um, and then then you have black keys on a piano as well as white keys. So you're going to have seven white keys per octave and another five black keys per octave. The black keys are just the semitones that fill in the big tones, the full tones of the white keys. So you get the idea. There's 12. There's 12 intervals. And what's interesting about this scale, I think this is an accident of the number 12, actually, pertaining to these harmonics. It turns out that that having 12, there's only certain numbers of divisions of the octave that produce what sounds like music. In Western music, it's 12. I think in other cultures they use different numbers. I think in India they use 19. I think in some countries they use only five or seven. But there's certain pleasing ratios that produce what sounds like music to us. And you probably notice Indian music sounds a lot different from American music, from Western music. It sounds kind of whiny, and the chords sound different. Well, that's because they have a different. They don't use 12 semitones. They use like 19, I think, and so it sounds a little weird, but it still sounds like music. But anyway, so this is what's called the Pythagorean scale. Notice that all the intervals here are rational. They're all fractions of integers. And it's nice that this sounds nice if you play in a particular key. Like if you're playing in the key of C. If you were playing this scale in the key of C, it would sound great. Problem is, what if you want to make a key change? Then it wouldn't sound so great anymore because these ratios aren't really constant. They're kind of close to constant, but they're not quite constant. So if you played it in a different key, it would sound pretty bad. So there's another type of scale that kind of corrects for this fact. It's called an equally tempered scale. And this is another attribute of that accident I was telling you about the 12 the 12 semitones. So all an equally tempered scale is just one where you go up by the same frequency ratio for each semitone. 2 to the 12th power, 2 to the power of 1/12, if you like the 12th root of 2. So if if you let the ratios of the frequencies of every semitone, say C to C sharp or C sharp to D, if you make all those 2 to the 1/12th, then that's what you get. That's what's called an equally tempered scale. And what's interesting about this is that you get close to these ratios, close to these simple fractions. If you did 2 to the 7th, 12th, let me go to the next slide because, yeah, here they actually work it out. So look at this. A fifth on the equally tempered scale. In the well-tempered scale, a fifth is a ratio of 1.5. These are all simple fractions on the right. This is the Pythagorean scale ratios, basically, on the right. But then on the left, you no longer get simple fractions. You get irrational numbers. Um, they're all fractional powers of two, with a 12th in the denominator. But you'll notice something interesting here. Like, look at the fifth. The ratio is 1.50000. That's a perfect fifth. That's a Pythagorean fifth. In the in the equally tempered scale, it's pretty close. It's 1.4983. And you can't really hear the difference. I mean, I guess if you're a music expert, you could. But most people can't really hear the difference. I can't. I'm not a huge music expert. I love music, but I don't think I could tell the difference between a song played on a Pythagorean. By the way, I don't think people use Pythagorean temperament anymore. This is another thing called well-tempered. I'm not going to talk about that, but well-tempered has the same disadvantage as the Pythagorean scale, and that it only sounds good in one particular key, or maybe a few particular keys. So equal temperament, I think, does the best job of being as versatile as possible in terms of, sounding good on every key. Um, and so you'll notice some of these other ratios are close to what they should be. I mean, the fifth, 1.2599, that should be 1.2500. The fourth, 1.3348, that should be 1.3333. So they're pretty close. And for all practical purposes, you can't tell the difference. And it has the advantage that you can change keys. And I think that makes music sound a lot more interesting. If you can change, I mean, even Bach did a lot of that. Bach liked to change keys in his music. I think he was one of the first composers who did that. And he also did all these fugues and inversions. And he was very his music is very mathematical. Bach is actually one of my favorite classical composers for that reason. Uh, but anyway, but I mean, most music you hear today, they do a lot of chord changes. They do a lot of key changes, which means that a well-tempered scale, Pythagorean scale, would make it sound really bad. But using an equally tempered scale makes it sound pretty good. Uh, I think I just want to say one more thing before I get off of this. Uh, I watched a video on this. I mean, there's a lot more I could say about this. I'm not a music expert. I've never tuned a piano. But I kind of know the mathematics behind it. But I watched a really excellent video a few months ago where the guy who made the video, he was saying, we could even do better than the equally tempered scale. I mean, now, everything's computerized now, right? I mean, well, we might as well just use all computerized instruments now because they can make them sound exactly like the real instruments. There's probably a lot of people that would argue against that. But if we could do that, we would have a big advantage because then we could program our instrument to make a chord change, a key change, and change the notes a little bit. So we could actually be playing, more like a Pythagorean scale in each key we're doing, and I think that would make the music sound a little bit better. Probably not that much better, but probably noticeably better. And maybe that'll happen in the future. I don't know. Be interesting. It'll be interesting to see what happens to music in the next, I don't know, 10, 20, 30 years. But anyway, that's my video. I hope you enjoyed it. Thank you for watching. Long live math, and I'll see you guys next time. Bye.